Now, how to compute free evolutions using transfer functions. We saw before how to compute h of t starting from h of s. Now we go to free evolution of t starting from h of s. In a certain sense, you know that in frequency, this is this object here, true? The way of working is the same as before. In the sense, we go here. We have this. We Laplace, and we write things like y of s is equal to something. How clear is this passage here? Very much, not at all, kind of. Now we are looking at the free evolution. True? U equal to 0, initial condition different from 0. Perfect. How do we do it? And it's the same whenever we have higher orders. It's the stuff as before. And we have an object, we have y of s, y free evolution of s is equal to numerator of s, denominator of s. You see? Numerator of s, denominator of s. We do the partial fraction decomposition. We might either write it in this way or write it in this way. We take this right-hand side and we decompose it into elements. Why? Because every element of this sum will be in the lookup table, and I will be able to inverse Laplace. So eventually we take Laplace, we go into numerator divided by denominator, we do the partial fraction decomposition so that we get sum of pieces, and each piece I can inverse transform. It's as before, true? True that it's as before? You shall know how to do this operation. There's the trick for single roots, that is the cover-up methods that I do not know if you know. I think that you have been doing, at least in high school or maybe in Math 10 or Math 2, this one with the system, true? Whenever you get the generical one, you got like the system. Are we together on this? If I have 7s minus 3 divided s plus 2, s plus 4, dividing it into a s plus 2, b s plus 3, s plus 4, sorry. Finding this and this, you know the cover-up method? Maybe not. To find this number, how do? I have to compute something related to this pole, so I cancel it out, okay? Then this pole here corresponds to s equals to minus 2. I put minus 2 here, and I put minus 2 here, and I get minus 14 minus 3, that is minus 14 minus 3 minus 17 divided by plus 2. This is the number, okay? And for this one, what do? I remove this one because I'm computing this. And then I put s equals to minus 4 here. So s 7 minus 4 times minus 4, minus 28, minus 28 minus 31, minus 31 divided by minus 1, so it's plus. How much are we together? Do you see it? How to do it? Very easy. It works whenever we get powers of ones here, okay? If I have a power of 2, this, or 3, or 4, whatever it is, I can't use this method. Okay? Summarizing, I take this object, I do Laplace, and I do everything in Laplace. I obtain this object here, I decompose it into something s minus lambda 1 plus something s minus lambda 2 or plus something. Every object has to be in the table of the lookup tables of Laplace transforms that I can do, okay? And then I invert, okay? Are we together, people? From a procedural perspective, this stuff here should be very clear and very obvious, okay? Maybe we don't go through this Python code here because it's kind of easy. Maybe I go, instead of looking this stuff here, if I have what do I expect to have in my h of t? Which signals do I expect to see in my h of t? I have this signal here that is going to be something e minus 3t. True? Are we together on this? And this one is going to come from the partial fraction decomposition because it's kind of decomposing the stuff into objects. Okay, are we together on this one? I cannot see it immediately. I have to do the partial fraction decomposition. Are we together on this, people? 1, 2, 3? Perfect. Then, whenever I do the partial fraction decomposition, will I get this or will I get also this? In general, I get also this one. Whenever I do the partial fraction decomposition and I've got the powers, either I write this as something s plus something, or I write as number, and here there's another number. Shall I make an example? Now, let's hope that I'm lucky with the numbers. Now, this has to be, let me go, I go here. This has to be a s squared plus b s plus c s plus 3. And this is equal to a plus bs plus cs squared divided by s squared s plus 3. This stuff here has to be equal to this stuff here, so it means that how is it possible? Because I'm completely dumb, because I'm very dumb, sorry, because I'm extremely dumb, because this is a s plus 3 plus bs s plus 3 plus c s squared. I was forgetting to put this stuff here. I do not know if you realized that I was forgetting to put that stuff there. I realized that that was not possible. So why this case here was not possible? Because I would find c equals to 0, true? C equals to 0 means this one disappearing, but here I do not have anything that cancels out with this one. You see? Are we together? This type of double checks in your mind. I see a puzzle face. Do you see? No. Okay. So going back to this object here, now we have C plus B has to be 0, true? Then 1 has to be, because this one is the s squared, the s power of 1 is 1 has to be equal to a plus 3b, and then I've got to have 4 that is equal to 3a True? I don't know, something like that, okay? But we get the numbers, and pretending that we solve it, we might get something that looks like 2 minus 1, 4. I'm throwing round numbers randomly because I don't want to waste time in that way. You got the system, and then you know how to solve the system. That shows you that in general, whenever I have something and this stuff here, I have something s squared plus something s plus something s plus 3. Okay? Whenever I've got a power, I get all the smaller powers in the partial fraction decomposition. How much are we together, people? 1, 2, 3. Perfect. Let's go back to the stuff that was interesting at the beginning. In case I have these y of s, of h of s, or whatever it is of s, if I go back to y of t, which signals do I see? I have some, let's make it a, b, c. This is going to be c, e minus 3t. True? Are we together on this? Plus b step. True? Plus a, what is this one? What is 1 over s squared? If 1 over s is a step, multiplying times 1 over s means integrating. That is a ramp. Okay? Together. System, I find this, I find this, I don't know, minus 3, 0 0.4, 9.2, whatever it is. And I have it. Okay? Go. Do this one. Do this one. Go. Let's see if we're together. Pen and paper, do it. I don't want you to mention. I want you to do. It's important to see if everything is. How are we, people? Are we there? So, how much is the procedure clear? Very clear, kind of clear, not clear at all. Where are we? Okay, I got as a result this one, that is those two signals for t bigger than 0, 0 otherwise. You got it, you would have gotten it you think you wouldn't have gotten it? Okay. Questions, people? Question.
Why are we talking about this method now that you're starting the pre-evolution, not before? Like this type of situation now and not before, when we were just like going from HLS to HLS.
The same. It's the same.
Or is it because we are going to encounter this kind of like Laplace function just when we evaluate?
So in the course, from a structure of the course perspective, I wanted to kind of make use partial fraction decompositions only after that we were doing Laplace transforms, and I wanted to do Laplace transforms only after that we got an intuition about stability, how the properties of the systems are.
No, I mean this kind of situation when it's not like just like exponential plus cosinus, and here we have to do this kind of function decomposition. Like we're considering this just when we evaluate the evolution with u equal to 0 and initial condition equal to 0.
The procedure is the same. Now we are going to go through forced responses. It's going to be the same. Eventually, we have y. So, in a certain sense, if we do Laplace, we will have y of s is equal to numerator, denominator, and this is going to be about the free evolution, plus numerator and denominator, and this is going to be about the forced response. We are going to do partial fraction decomposition here, partial fraction decomposition here, and then we will get everything. Almost always, not always, we are going to be seeing an exception very soon, but somehow 99% of the times we are going to do this operation here. We express the total y as polynomials, partial fraction decomposition, lookup table. Okay. Not always, we will see very soon that there's an exception, but somehow very often. Other questions, people? No. And then let's stop.